Well, welcome back. This is Math 3163. This is the last of the lecture videos. And in this video, I'm going to be reviewing for your final exam and talk about what's going to be on the final exam and what's the best way to prepare for it and stuff. So let's take a look at what we got here. All right, so if I was preparing myself for this final exam, as with all good math classes, you should first go back and take a look at your test 1, 2, and 3 and kind of clean up the mistakes that you made on that, figure out what mistakes you made, and be prepared for that. Also, go over the old homework sets, and I've got the videos are still up there. Watch those things on the homework sets, making sure you've mastered the homeworks and stuff. But I would also, like I said, most important, is go back and take a look at test 1, test 2, and test 3, and any kind of problems that you missed on, go back and see if you can figure out what the problem was and make sure that you have this thing mastered and stuff. The other thing that I would do is make sure that your notes are complete. You should be taking notes on everything that we do in terms of the class and all these awesome videos that I've been making for you guys, and make sure you're taking excellent notes off those things, especially the proofs, especially the definitions, and some of those major theorems that you need to know. Also, remember, I am going to turn off the videos during the final exam. So you're not supposed to actually have that kind of access to anything. You're actually not supposed to have any access to anything online whatsoever. Because of the situation with the COVID-19 and orders of the university, you can only have your book and the notes that you take, and of course your TI-84 calculator. No internet activity is ever allowed while you're taking the test and stuff. We will be monitoring the Canvas site as for similar wrong answers. The university has got this new system that they're trying to implement in terms of monitoring systems, and also it actually can read your PDF files and stuff like that to look for anomalies and the like, especially for the same wrong answers and things like that. So we're working on some new technologies right now as we speak. So you're not allowed, this is considered cheating when you actually go and you know, obviously any kind of discussion between students or anything like that, but it's also considered wrong to actually have any internet activity. And I want to talk about that a little bit, because on this last test, actually, excuse me, it was test number 2. We're still grading test number 3. It was test number 2. We saw a lot of internet answers and stuff. People are, like, my definitions were actually, looks like several students went to Wikipedia and actually were copying down the Wikipedia definition, which didn't even make sense. Talked about monoids and things like that. We haven't actually discussed monoids. And officially, you're supposed to fail the class and fail the exam for that, and the test as well. But I just took off some big point totals, and I'm going to warn you about that one more time. You're supposed to use your textbook and your notes only. Don't sit there and try to Google something or other, try to figure out what the answer is. Probably the answer is going to be wrong when you do that, or it's going to be overly detailed to the point where we'll definitely know you cheated and stuff. So not the way to go. All right, so let's talk about what I plan on putting on the exam and the things I will not put on the exam. Yes, the exam is going to have definitions on it. So you need to go back and look at all the different types of definitions we've had. Now, we didn't have very many definitions except for the usable ones from chapter 1. But when I got test 1 that is, but when I got into test 2 and test 3, everything from subrings, from different kinds of rings like commutative ring with identities, integral domains, fields, and then don't forget all that stuff we covered in test 3 material on ideals, prime ideals, principal ideals, maximal ideals, cosets of quotient rings, congruence classes, different types of congruence classes. So there's lots of different definitions, units, zero divisors, so many definitions. Make sure you go back and take a look at all the definitions that we've covered, and make sure you've got a textbook or things that we've written down in the class similar to the textbook type of definition, not any monoid crap off the internet. We haven't discussed monoids. It was the definition of a unit, and several students put a word about the inverse of a monoid, something or other. That man, and we looked that up. That was a Wikipedia answer, and honestly, you deserve to fail the class with crap like that. But we didn't, but if I ever see it again, I surely will fail you. All right, so let's keep going here. Got to know your definitions. You also need to know general questions about the types of rings, so and including quotient rings. So how do I figure out what type of ring I happen to have, especially if it's a finitely generated type of ring that you have only a finite number of elements in there? Check out that multiplication table. That tells you a lot. See if it commutes or doesn't. See if you have an identity or not. So forth and so on. See if you have any zero divisors. See if all non-zero elements are units. See if you've got a field or got an integral domain, so forth and so on. We're also going to have about 8 proofs on the exam. The final exam is typically going to be a little bit longer than our test, but I'm not making it that much longer. On average, you had around between 5 and 6 proofs, typically 6 proofs on your tests. So between 5 and 6, so I added 2 or 3 more to the actual final exam. Your final exam obviously will be on Wednesday, and I believe that is the June 24th, and that is going to be from, it starts at 3 o'clock like our usual test goes, but I'm going to give you some extra time on that one. You're supposed to have 3 hours, so it goes from 3 until 6 p.m. Officially 2.5 hours, but I'm going to lengthen it to 3 hours for you guys because I gave you the full class period. So what I gave you on the test was like you're supposed to have 2 hours. I gave you 2.5 hours. Final exam, you're supposed to have 2.5 hours. I'm going to give you 3 hours, so that would be until 6 p.m. And then I will probably add on maybe just a little extra time at the end, maybe another 30 minutes or so at most, to make sure that you get this thing uploaded to the internet, because if it's not uploaded on time, officially you have not done the final exam, and you can pretty much see what happens to your grades. So pretty much I'm going to go from 3 till 6 with an extra 30 minutes, so it has to be uploaded by 6:30. That's what I plan on actually setting up the exam. I'm trying to buy you guys a little extra time because you do have to do a little extra work on scanning it as a PDF file, as a single PDF file, and then uploading that to the actual Canvas page. So, and it's got to be done on time. 6:30 will be your deadline on this stuff. All right, as we continue on, like I said, what kind of proofs are going to be in there? Well, I'm going to do a mixed bag of proofs because obviously from test 1 through test 3, from chapter 1 through chapter 6. So you are going to have some integer questions. So pay attention to what I'm telling you. Let A and B and C be integers versus let A, B, and C be elements of a ring. Also, I could have A of X, B of X, and C of X. Now they're going to be elements of a polynomial ring F adjoined X. Also, don't forget that understanding the concepts of quotient rings and congruence classes of rings, mod an ideal, making quotient rings and the like, as well as F adjoined X modded out by P of X type of quotient ring. Also, remember your isomorphisms and homomorphisms. That goes back to the definitions, as well as we did a lot of proofs about that. We actually, on a homework problem, we did the zero divisors, map to zero divisors on the homomorphisms, subrings map to subrings, ideals map to ideals. Homomorphisms are property preserving. So definitely know how to prove a subring. That was theorem 3.6. Make sure you know how to prove an ideal. That was theorem 6.1. And those theorems I am going to put as reference on your test, on your final exam, like I did with the test. I'm going to take kind of all my little reference theorems from test 1, 2, and 3 and make one big reference sheet for you guys, so you don't have to kind of flip through the book to quote theorem 6.1 or theorem 3.6. It'll be on the last page, just like your test had been. Again, and also denote the different types of congruence. Congruence modulo n, where n's an integer. Congruence modulo p of x, where p of x is a polynomial and f adjoint x. Congruence modulo I, where I was an ideal, something completely different. A is congruent to B mod I meant that A minus B is an element of I versus a polynomial. A of X is congruent to B of X mod P of X means that P of X divides A of X minus B of X. And we also had your integer congruence classes as well. The best way, again, to look at the type of proofs I'm going to give you is go back to the test and the homework sets and some of the proofs I did in class and making sure you have mastered those things. You may see something very similar on the test. In terms of the non-proof stuff, All right, make sure you can write out the cosets of a quotient ring. So if I give you R mod I, like I did on your last test, something like Z18 mod I want you to write down what all the cosets are of that particular quotient ring. I will actually list what the quotient, the actual ideal is going to be, so you can write out the quotient ring. I want you to find all equivalence classes of f of x modded out by p of x. You know, you're dividing it by p of x, so your quotient rings are going to be the congruence classes of the remainders. Okay. You also don't forget your other equivalence classes are those z mod n, so that's from 0 through n minus 1. It's the remainders when you divide by n. And also be able to identify what kind of ring it's going to be, especially when you're modeling out by a polynomial. If the polynomial is irreducible, another one of those definitions you need to know, then f adjoint x modded out by p of x will be a field. But if your polynomial p of x you're modeling out by is reducible, and make sure you know how to find if it's reducible or not, then f adjoint x modded out by p of x will actually be a commutative ring with identity. Number 3, the other one, I'm going to throw some stuff at you, just reminding you way back when in test 1, chapters 1 and 2, I gave you some algebra or arithmetic, if you will, to solve for x in Zn, Z mod 7, Z mod 8, if you go back and look at your test there, and be able to solve for x in a different world than just regular real numbers and stuff. And also, the last thing is, don't forget to know how to use the Euclidean algorithm to find the GCD of two integers or two polynomials or whatever the case may be. And I'll talk more about that in just a second. Again, I will provide you with the reference numbers and sheet of the theorems that you can use for your proof. So the reference theorem numbers and stuff like that. So if it's not on the sheet, don't use it, because I've had a lot of folks, like on the homework set, that I asked you to prove, you know, a of x is congruent to b of x, something or other, that actually was the statement from theorem 6.1. So people want to go, well, by theorem 6.1, it's proven. No, I didn't. That's not actually stating the proof. I want you to actually walk through the definitions of congruence, definition divides, and give me an actual proof of this thing. Don't quote me what theorem I'm actually trying to get you to prove out of the darn thing. That just kind of defeats the purpose. I want to see the proof written up properly. So, that being said, what's the best way to study for the final exam is actually looking at the your old test. Well, how do I know if I got a problem wrong? How do I know I'm going to get it right? I've already heard the questions in my mind on that. So I decided to do this. Now, I don't publish my solutions to the test, because that's just wrong in so many different levels of actually being a professor and stuff. But I thought I'd do this. You know, to save yourself some time and stuff like that, I would actually go through this thing and actually show you what the answers that I wrote down on my answer key. I'm not publishing them out that you actually have a hard copy of it, but they're going to be on this particular video. And so you look through your test and see which ones that you missed out on, and then you can go to the actual video. And remember, there is a pause button on this thing, so you can freeze frame that sucker and figure out what you got a mistake at and stuff like that, and then continuing on. So that's kind of my plan for helping you guys out and kind of making sure I do not violate any kind of university professor status of publishing answers to tests and stuff, but I will at least show you what the answer is, so you can freeze frame the actual exam this particular video. But again, you shouldn't actually freeze frame everything and write everything down again. That's going to be a lot of extra work. Only focus on the problems that you missed. Study the problems that you got right and just make sure you know how to do it, but study the problems that you missed especially. So here was our test number 1. All right, test number 1. Oh, go ahead. See, this first problem was a disprove. I'm not going to make you do any disproving on the test. That was chapter 1 on coming up with counter examples and stuff. I'm not going to put a disprove problem on the test. This is a writing intensive proof class. We're going to be focused on proving, not disproving, but you understand the concept of disproving. Here was a great example right here of that first basic definition of showing, you know, two integers divide each other. So show that A divides GS plus HT. So here's my classic proof of that. And remember, you can pause it. So I'll keep going. The next one was another classic. These were all integers. This was test 1. So given the GCD, remember you got two options with that, and I went with the theorem 1.2 option to show there exist integers, u and v, write my equation, so you can prove that h divides k. Notice this was a short proof. Here's another 10-point problem proof there. This one right here is the proof. We're going to show that c divides kb, and again we were given part of it was the c divides ab, and k is the GCD of a and c. And remember, GCDs, you got two options. Again, I went with the theorem 1.2 option to get my big equation on this thing. And this is the general statements of what I was looking for. I mean, these are my proofs. Now, you've got to be a little more writing intensive on the thing, but these are the points that we were looking for. And number 4 was we were supposed to show that we were given that f is congruent to t mod f, and g divides f. You wanted to show that s is congruent to t mod g, and by definition it divides, and by definition congruence, you got g has to divide s minus t. So there's my proof on that one. Again, don't forget the pause button. Here is one that several students messed up on. It was problem number 10, because you had to do a particular trick on this one. Anytime I give you a GCD of two elements, whether it be polynomials or integers, is equal to 1, you definitely want to do the theorem 1.2b option on this thing and come up with that big equation. And then typically you multiply whatever you want to divide by on both sides of it, and then do your substitution. So there's the classic proof of that. Here was another one that a lot of folks messed up on, and just here was the idea behind it. You wanted to prove that if p was prime, so you got all that definition of prime integer stuff that you need to know, and p divides both a and a squared plus b squared, then you want to show that p divides b. Well, no problem there. What you end up showing through your work with your manipulations of your definition, divides, and substitution is that p ended up dividing b squared. But if you look at your reference sheet, when a prime divides a product, b squared is b times b. When a prime divides a product, it either has to divide the first guy or the second guy, but the product is the same thing. That was something we proved, actually, theorem 1.5. You may want to go back and look at that, and so that's why p divides b. And that theorem 1.5 was actually on your reference sheet there, but we actually did prove that one in class. All right, here's a non-proof problem here on writing out the multiplication tables and the addition tables on Z mod 8. I probably won't get you to do this. The addition tables is great, but it's just basically killing a bunch of time there. The multiplication table, that's something you need to know how to do, because that actually tells you what kind of ring you're going to have. Since I got zeros inside the big block here, this sucker has 0 divisors, which makes Z8 actually a commutative ring with identity. It commutes, so the main diagonal, they look exactly the same. 2 times 3 and 3 times 2 are the same numbers. But the fact is they have 0 divisors in it, so it's not an interval domain. And here were the answers to the solving in Z8 and Z7. Remember, Z8 was not prime, and when it's not prime, you get multiple answers, no answers, and possibly one answer. With Z7, 7's prime, so this stuff's a field. When you have a field, this Z8 was actually a commutative ring with identity. But when you have a field, you're guaranteed to have one answer until I start giving you guys quadratics and the like. That's when you can have your multiple answers. But the trick on the quadratics was basically you set this thing up in an equation and you just plug in your Z7, 0 through 6, and you see if any of them actually give you the answer on the other side. And then to pick the ones that do, and you win the game. So. Here was your Euclidean algorithm on doing the classic shift. So you divide one into the other and write it in the division algorithm format, and then the quotient becomes the dividend, the remainder becomes the divisor, and you set it all up again, and you keep on doing it. And remember, just before 0, when you get 0, the remainder before the remainder of 0 is the GCD. This was Euclidean algorithm with integers. We also had a Euclidean algorithm with polynomials, and the GCD polynomial that works the same way had to be monic. And finding the U and V, I'm not going to put that on the test. That's just working the theorem backwards, and so many people screwed up the algebra on that one. I just don't want to see that again. So this will not be actually on your final exam. And here's, some of the theorems that we actually listed. I will take these and add them to test number 2. Here's your test number 2 solutions. And I also put a bonus question on there, so Merry Christmas on that. The definitions. Now, this is the one that I'm angry at several students about. And it wasn't just one, it was several of them that went and looked up the word unit in terms of the internet because, one, it's cheating. Number 2, it's lazy. You got your textbook, read the textbook, it's right there. And so so looking up and using the word monoid, it's an invertible element with a monoid or something or other that came up with. And that's deep, and that actually has more information than I needed, and it's not actually the textbook definition. So when you do stuff like on Wikipedia or looking up stuff off the internet, that's illegal, and that's worth being thrown at a university for. But I did not. I just took off some big points on that thing because I could tell you did not use the textbook definition, the definition we had in the book. So here's the definition of a unit. Here's your definition of an integral domain. This one was a classic one right here where you had to prove that if you had a homomorphism that units map to units, B was a unit in R, then sigma B is a unit in S, and so here's your proof of that. We also did in the proof, so if you go back to your homework set, you also have the proof that zero divisors map to zero divisors, so don't forget that. And speaking of zero divisors, that's another one of our definition. And definition of a ring homomorphism. And don't forget, I didn't put them on there, but you may also be required to know the definition of a ring isomorphism. So it's the homomorphism with the injective, surjective stuff. Your definition of subring, not theorem 3.6. 3.6 is actually how you end up proving it. So it's the subset itself that under the same addition and multiplication are itself is a ring, then you're going to have a subring there. So there's my classic definition of that. Here was a classic. Now we're in the wonderful world of polynomials. So if you notice, what I really did there was take a bunch of the examples that we did in terms of integers and just put a big old X on them and make them into polynomials. So here's your proof of number 5. This one right here was one that a lot of people cried about. It was proving somebody's a subring. Subring, so we're going to be quoting theorem 3.6 on this guy. And the trick on proving subrings and ideals is, honestly, it is the idea of being able to read the set notation. So let's take a look at this guy real quick here. Let C be equal to the elements R, little r, element of big R, such that little r times W equals W times little r, where W is fixed in R. So you actually have 2 concepts to be inside of C. Where do you come from? And what property do you have? Number 1, you come from R. And it's the same element. I didn't introduce any new elements. When you introduce new elements, that's when you actually want to do subscripts. So they're not subscripts here. No need for subscripts. So I had a bunch of folks that start out like this. And let me explain. They did this. So they first tried to show 0 was in the thing, and that was the small point total, because 0 pretty much commutes with everybody here. So 0 times W equals W times 0, which equals 0. So 0 is in C. So that's the easy part. The big point totals were in these closed under subtraction and closed under multiplication. So a lot of people did this. Let me explain what not to do. Let X and Y be an element of C. That meant that X and Y were an R, and there exists an R1 and an R2 such that X is equal to R1W, which is equal to WR1, and Y is equal to an R2 times W, which is equal to W times R2. Well, you've already lost the structure of what it means to be inside of C. X and Y aren't in C. The actual what you came up with, that R1 and R2, those are the dudes that are in C. So when you came up with that, everything else you wrote after that is actually wrong, because it's not the setup for what it needs to be inside of C. To be inside of C, if you look down here, I'll come up here. Let X and Y be an element of C. That meant that X and Y were an R, and with the property, it's the same guy. So X is replacing R. So XW equals WX, and YW equals WY. And then you can go through the rest of it. So here is the proof of number 6. Number 7 is one we actually did in class, and I just thought it would be a great problem to stick back on the test. And it was the idea of, remember we defined what a kernel of a homomorphism is. It is the set where all the elements are from R that actually map to the 0 element in S. And that actually is a subring of R, and later on you discovered that it's not just a subring of R, it's actually an ideal of R. So we've done 2 different kinds of proofs of this particular guy, so that's definitely worth noting here. So there's your proof of that guy. And here was another great example, and again a big point total where a lot of folks lost some points on this one, and it was the idea of under homomorphisms, subrings map to subrings. On this one, I gave you a homomorphism, R to S, and I told you that W was a subring over there in S. M are the set of elements, little m from R, such that phi of M is equal to W for some element W in W. So I introduced a new element. That's a great time to use a subscript here, but we're going to prove it's a subring. So here's the deal. It's all the elements to map to the W elements. So when I start out with my X and Y, this is where most people messed it up at. When you start out with X and Y and M, that meant that X and Y came from R, that's where you come from, such that there's going to exist a W1 and W2 inside of the W set, such that phi of X is equal to W1 and phi of Y equals W2. Remember, big W was given to be a subring of S. And then we talked about the subtraction, and then we talked about the multiplication to show a subring. So there's your proof of that one there. But it's in that set structure that a lot of people lost some points in. If you get the set structure wrong, the proof, the whole problem ends up being wrong, and people get upset with, well, how many points did you lose? Well, you lost most of them because the set structure is wrong, so everything you wrote after that is wrong. All right? This one is, again, a classic one where I changed integers to now polynomials, but we got a GCD. So with GCD, you got 2 options. Definition of GCD option, or you also have now, instead of theorem 1.2, it's called theorem 4.8, where you can get big equations out of this guy. So I gave you 2 GCDs, and then you were supposed to show that T of X times P of X divides Q of X. So here's my proof of that guy right there. Now, when it comes to the actual test and stuff, I'm not going to make you prove anybody as actually as GCD. We did that on one of the homework sets, and that was a very large proof right at the beginning. It takes a lot of effort to actually prove somebody's a GCD because you have to quote corollary 1.3 or corollary 4.9 out of your textbook there. All right, here was a big old polynomial, and you wanted to factor this big polynomial as a product irreducible, so you definitely want your calculator on this guy. So the first thing to do, since my field is Z5, I checked all my elements in Z5, 0 through 4, and I look for the ones that give me 0 back in Z5. None of them gave me 0, but when you convert it back to Z5, 2 of them did, 1 and 2. So there, and I use synthetic division on my polynomial to get the remainder, but I have to convert them back into Z5 coordinates. Then I take my other 0 and do the synthetic division on that, and then I get my answers, but I have to convert it back into Z5, and then I get the polynomial x minus your c x minus 1 times x minus 2 times the resultant polynomial. But I can't just stop there. I've got to double check to see if I have any double roots. So I'm now going to focus on this polynomial, and the only numbers I have to actually check are for double roots are the original roots, 1 and 2. So into this polynomial, I called it g of x. I plugged in 1, did not give me a 0, but when I plugged in 2, it did. So I take 2 and plug into the g of x and reduce him, and then I double check him one more time. I call that guy h of x, 2x squared plus 2x plus 2, but 2 did not divide into it, no remainder there, so this ends up being your polynomial. But you got to put the elements in Z5 adjoined x, so you're not officially allowed to have the minuses. So in Z5, just add 5 to it. X minus 5 is the same thing as x plus 4. X minus 2 is the same thing as x plus 3, and the rest of polynomial. And you could have factored out the 2. That would have been fine too. Find the GCD of polynomials. In terms of this guy here, you had to do the long division. This was the bonus question. And again, I saw so many mistakes on the long division part of a lot of students and stuff like that. The real deal was that you had to make sure that your polynomial, once you got the polynomial 0, and this is classic for me, I typically do about two or three divisions, and then you should be getting a remainder of 0 by that time. And the remainder before the remainder of 0 is almost the GCD, but you have to make it monic. This had a leading coefficient of 4, so you had to multiply the entire polynomial by 1/4 to make the leading coefficient 1 to make it monic. So the answer was x squared plus x plus 2. Okay. So if you, I did give you some people some bonus points, even though they got it wrong because they forgot to make it monic. I did give you at least like 3 points or something other there. And now the last test here. Again, more definitions, and I don't want to see anything off the internet in terms of a definition. This is why you have your textbook and stuff, and most important, your notes. So the definition of an ideal, here was your definition of a prime ideal and a maximal ideal. So I hit all the big three there. The only one I didn't put on there was a definition of principle or a definition of a finitely generated ideal. The idea of how to add and how to multiply elements in a quotient ring. The coset elements are as such. Those were free points for everybody. I think everybody got that right. Make sure you know your theorem for 6.14 and 6.15 because it goes both ways. This if and only if. So if you have a prime ideal, you take a ring and mod out by a prime ideal, you get an integral domain. If you take a ring and mod out by your maximal ideal, you get a field. So, and it goes both ways. So if you got your quotient ring as a field, you must have modded out by a maximal ideal. If your quotient ring is an integral domain, you must have modded out by a prime ideal. So make sure you know those. Make sure you have the ability to, this is that non-proof stuff, of being able to pick out like a Z15 or a Z25 or a Z somebody. You make sure you can pick out what the actual ideals are going to be. Basically, it's the, and remember, an ideal never has the identity element in it. Once you get one in it, you get the entire set back again. And remember, those are not proper ideals. The proper ideals are the ones that are not 0 and not the entire ring itself. So you're looking at the multiples, things that are basically the GCD. It's the elements that with the GCD of that element in 15 should not be equal to 1. Those are the ones that end up generating the actual ideals. And once you pick an ideal, I did G15, I said I was the 0, 5, 10. Then you get the element 0 plus I, 1 plus I, 2 plus I, 3 plus I, 4 plus I, all the way up to the point of where you actually end up getting the next element in there. And then from that set, since this guy here was a maximal ideal, we only had 2 of them, so they're both actually maximal ideals. When you mod it out by it, you got a field. That's actually quoting theorem 6.15, if I remember correctly, on my numbers there. Here comes your proofs. This was number 6, where we had, you know, A of x was congruent to G of x mod B of x, and D of x was the GCD of A of x and B of x. I want to show that D of x divides C of x. So again, you're using the definition of congruence modulo H of x to be able to, excuse me, that's a B of x there, modulo B of x to show that you get your equation out of it. And remember, it's a 2-step process. The modulo means that B of x means that B of x divides A of x minus C of x, and then by definition of divides, there exists a polynomial, you name him, such that A of x minus C of x is equal to B of x, I called him M of x there, and then you kind of work the proof, and you're trying to get what that guy is. So here's another classic problem, very much like when we had integers. I just chucked a big old X on it and stuff. The next one was one, again, we've done before and the like in class. This is with the idea of taking the kernel of a homomorphism, and same thing that we did before. We first, in the last test, proved it was a subring. This time we proved it was an ideal. And remember, when you're going to start proving things are ideal, you're going to quote your theorem 6.1. You first show it's non-empty by showing zeros in there. You show it's closed under subtraction, so the 2 setups are exactly the same as subring, but it's the 3rd set. You pick one element inside the set and one element inside the ring, little r element, big R, and then you prove that the product is in there. And remember, if you don't have a commutative ring, you got to prove both ways. And so I've underlined, you see a lot of underlining here because that's basically me trying to describe the point totals, what we're looking for on this thing, to making sure everything inside the set has been actually satisfied. So we're looking for certain things when we grade this stuff. So there you go, and remember your pause button there. This was one that was very much like the principal ideal. This is the finitely generated ideal. This time that we're generating by the elements P and Q and R. So it was a great time for subscripts. So to be inside of G, you had to come from R, and you had to be equal to an element S times P plus T times Q, where P and Q are fixed. So for the S and T, so I used a lot of S1s, S2s, and T1 and T2s to be able to get the elements in there. So there it is, and it follows directly from proving a principal, an element generated by one element is actually an ideal called a principal ideal. Again, this is very similar in terms of I got two GCD problems, and we wanted to add them together. Excuse me, not for GCD. Excuse me, modulo h of x. So we got two congruence classes, two congruence mod h of x. And another one mod h of x. So I gave you that f of x is going to g of x mod h of x, and d of x is congruent to e of x mod h of x. I want to show that f of x plus d of x is congruent to g of x plus e of x mod h of x. I know there was a theorem on this in the book. Didn't care. I wanted you to actually prove it. Use the definition of congruence modulo h to talk about the divides, and then use the definition of divides to be able to get the equation. And did the same thing for the second part, and then you end up basically adding the two equations together to be able to get the actual, the fact is that h of x divides f of x plus d of x minus g of x plus h of x. So, and don't forget to state your properties and all your manipulations of the equations and stuff. That's the algebra part of this thing. This was a classic one on ring homomorphisms that we've done, where, in this particular problem, I gave you J was an ideal of S, all the elements B from R, such that phi of B equals K for some K in J. We're going to prove that's an ideal of R. So it's very much like the one that we did when we proved subrings map to subrings. We just had to go through a map that show that ideals map to ideals. And remember, with the two parts, because I did not give you a commutative ring, you had to check both, x times r and r times x to make sure both of them, xr is an I, and r times x is an I, and x times r is an I. So don't forget, again, classic theorem 6.1, got the proof here. And again, I'm underlining stuff, so pay attention to that of what we're looking for. Again, some more of the non-proof stuff with one more little proof there. This was the basically the equivalence classes in Z3 adjoint x modded out by P of x. Definitely want to know how to do this. Since you're modding out by 2x squared plus x plus 2, the remainders, when you divide by an x squared, you got to be x to the first, so it's ax plus b, where a and b were from Z3, so you got 3 choices of a, 3 choices for b, grand total of 9 of them, and make sure you can do that. And then, how do I figure out what kind of ring this guy's going to be? I'm going to look at the P of x and decide if it's irreducible or reducible. When I plugged in 2 into this thing, you noticed you got 0, which meant and back in Z3 it's 12, but back in Z3 it's 0, which means 2 is a 0, makes P of x a reducible polynomial, because P of 2 equals 0, 2 is a 0, therefore P of x is a reducible polynomial, which means this the quotient ring Z3 adjoint x modded out by 2x squared plus x plus 2 is going to be a commutative ring with identity. Remember, with this stuff of field adjoint x modded out by polynomials, you only got 2 options. It's either going to be a commutative ring with identity, or it's going to be a field, depending on the reducibility or irreducibility of P of x. Here was a classic one of understanding the definition of what it means when you've got R is a ring and I is an ideal. What is A is congruent to B mod I? It was a very short proof, so I only gave you a little bit of room and not quite the big point totals like the other ones were. But for A to be congruent to B mod I, don't tell me I divides A minus B. That ain't right. We're talking about modulo I. So where I is an ideal of a ring. So A is congruent to B mod I means by definition congruence modulo I that A minus B is an element of I. So in this one was straightforward here. So I gave you two of them. A is congruent to B mod I and C is congruent to D mod I. So A minus B is an element of I and C minus D is an element of I. By definition congruence modulo I. And then all I had to do was just add the two guys together. And because I is an ideal of a ring, it is a subring, so it has closure. So when you add them together, you can use your commutativity and associativity properties, and it's still going to be an element of I, but I have to put it in the right format because I want to show that A plus C is congruent to B plus D mod I, so I have A plus C minus B plus D is an element of I, and then by definition congruence modulo I win the game. It's a very short and sweet proof. And that was, and so with these particular corollaries and theorems, we should know to reference in our textbook. From a textbook for the test, I'm going to do the exact same thing. I'm going to sit there and take test 1, test 2, and test 3, and basically list them all in there on the last thing. So these are the ones you should be referencing out of the textbook. No other ones you really need. If it's anything else, you actually probably put it straight forward. And remember, you're not allowed to have any internet access with this stuff. Don't go look up definitions off the internet. You will definitely fail because our textbook has an interesting way of wording this stuff. We're not going overly high tech. Don't throw monoids at you or anything like that, like some Wikipedia crap will do. So hopefully this has been helpful. Again, I did go through this very quickly, of course, but the idea here is to make sure that you have the pause button. I can get through all of these little guys here. So you've got your little pause button there so you can look at them and basically focus on the ones that you got wrong. Review the ones you got right, but focus on the ones you got wrong. And like I said, you know when the final exam is. It will be on Wednesday. So good luck.